are honored to have with us our esteemed resource person, Dr. Gina Cleanangandi, Assistant Professor at Cochin University of Science and Technology. Dr. Gina specializes and she completed her PhD from National Institute of Technology, Calicut. Her research on semantic textual similarity using deep learning is highly relevant in today's AI-driven world. With her valuable experience in academia, research, and industry, including Wipro Technologies and Amrita University at Madai, we are confident that today's session will be extremely beneficial. Ma'am, we extend a very warm welcome to you.
Thank you, ma'am, for the opportunity. I am also excited and happy that I have got this opportunity. Thanks a lot.
Thank you, ma'am. I also extend a heartfelt welcome to all participants. Your presence makes this FDP meaningful and successful. Today's session is on transformers, BERT, GPT, and LLMs. These topics plays a crucial role in modern AI applications such as chatbots, machine translations, and generative system. Now, I invite Dr. Gina Cleanangandi to take over the session. Ma'am, over to you.
Okay, thank you, ma'am. I shall share the screen now, and you can just tell me whether you're able to see it, so then you can start.
Okay.
So is the screen visible?
Yes, ma'am.
Yes, ma'am.
Okay, thank you. So, welcome participants. So glad that I can see that it's a huge count in the meeting. I'm extremely happy that so many are attending this on a very extreme hot weather, and most people would prefer to sleep, take rest after a heavy lunch and like that. So let's learn something new. And by the way, it would be nice to have an interactive participation throughout, because see, online FTTs are normally meant to be boring. Not meant to be boring, but most of the time what we see is people just switch on that meeting and then do whatever work they want to do. And the faculty or the resource person have no idea what is happening there. So please, if you are listening, interact. Don't think that someone else will respond. Your response is very valuable. Only then I can understand whether I should go more deep into it, or whether it is okay and all. So it's very important that you respond to the queries. And unfortunately, when I'm on a full screen, I won't be able to see your responses in the message box. So you can just unmute, ask something, and I'll try to join my phone also, so I can read the messages. Just a second, I'll try. Okay. And you can try to join in a companion mode so that I can read the messages. Just a second, okay. Okay, so that's 100 plus participants. That's a huge number. So let's see how many of you are actually listening. So can you put a hand raise? Just now, people. Thank you, just now. 24, 25. Okay. So that is 1/4. Okay, so we'll start. So today's topic is transformers and large language models. See, this is actually it's a very vast topic. Okay. Here in FISAT for second semester MTech, I offer this as a course. Okay, a 6 months full semester course on transformers and large language models. And this is 1.5 hour plus talk. So my plan is I'll talk for 1.5 hour, and half an hour we can have discussions and doubts clearing sessions. So in 1.5 hour, what we can cover, that is something that has to be thought of, because that's two way we can approach it. We can just go to the very foundation, talking about the math behind it, about the neural networks and all those things, or we can look it from a bird's eye view, where we can look at many things like architecture, where it is applied, and why it works, why it won't work, when you use it, how you should be, what all you should be careful about, where all can you use it. And my choice is the second one, because it's very important to know the basics, but on a first day, I think that's not the way to go. So I'm hoping that through this talk, you will get an overall idea about transformers, and you will be fascinated about this language models, fascinated enough so that you will go and look into the math behind it. Okay. So instead of me putting that maths down your throat, I want more of yourself. So this talk will be mostly about, I'll be introducing you to large language models. I'll be talking about the language modeling problem, which is a very classic and very popular NLP problem. We'll talk about various tasks that LLMs can handle. We'll just give a very brief overview about transformer architecture, and we'll talk about two very famous pre-trained models, BERT and GPTs, and we'll also talk about risks of LLM. So this is what I'm planning to cover in this talk. But maybe some of you are more interested in these. You might have learned some courses on LLMs, or you might be teaching some course on AI and all, because what I understand is most of them would be teachers. And there might be some doubts that you want to ask. So you can just keep it there, and we can discuss everything at the end of the talk. Okay, but others, like whatever topic which I am covering, you can stop me in between and you can ask doubts regarding that. But what is not being covered in the topic, I'm still willing to answer those, provided you can hold it till the end of the session. Okay, I'm saying this because most of the time I start taking class, and then suddenly there is one or two participants who are very expert in this, and they will start asking questions which most probably others won't even understand what the question is, and that really puts them off. So this is my plan. Oh my God, audio is not proper. Audio is not proper. Okay. Maybe I'll just avoid this bit. Just a second. I think without the mic, it will be more clear. Hello. Yeah, this is me without the mic. Can someone just respond? Is the audio still breaking? Is the issue with the internet, or is it my microphone? How's the audio just now? Yeah, it's clear. Okay, thank you. Problem was with the headphone, I guess. Okay. Okay. So that's the plan. So bird's eye view on transformers and large language models. And you can just, something which is not covered in this, you can just note it down and we will discuss it in there. Okay, thank you. So language modeling is a very typical NLP problem. Okay? In the name itself, it is the language models. But it became this popular, like now, not just the NLP people, everyone is talking about language models, image, speech, bioinformatics, video processing, and generative AI. Everyone is talking about large language models. And see, this excitement is very recent. Even though language modeling was like goes decades. The first statistical language model, it was introduced like in and this much excitement happened with the coming of certain events in the late 2020s when language models started winning programming contests. Okay. See, AI, we all know that AI is a very age-old problem. Okay, people have been talking about, there has been movies, fictions, stories about AI taking over the world. It has been around for quite a long time, but no one actually believed that it's going to happen. It was just stories. And it was in late 2022. See, 2022 is very recent. People started feeling that, okay, something great is going to happen. And some of the events that really led to it is when LLM started writing programming codes by just reading the description. Okay, so this is a programming contest where there is a requirement that is given in language, natural language, and you have to read the requirement and you have to code. This is meant for human beings. Okay, and then they understood that language, this AI was able to achieve top 54% something. Okay, now it is not 54. I'm talking about an old story. Now we know Google Copilots, which can, we know, right? We are always talking about people losing job. Programmers are not getting hired because AI is taking over their job. Okay, but 3 years back, this was something, even getting a 54% was considered as a exciting thing to happen. Then another thing which brought this excitement in was the theorem proving ability. Okay. Everyone is saying that, okay, language like AI can do like things like normal things, but proving maths, usually that is what that's how we measure intelligence, isn't it? So when a student can do very good math problem solving, or they have some mathematical skill, we say that, oh, that student is very intelligent. So AI started solving mathematical problems. And again, that was in 2022. So at that time, all these papers were breakthroughs. Okay. Then it started writing poetry, okay, where we were saying that, okay, no matter whatever advancement AI brings in, creativity is something which only human can possess. Okay, only like creativity is something very human. മനുഷ്യർക്ക് മാത്രം പറ്റുന്ന എന്തോ ഒരു കഴിവാണ് കവിത എഴുതുക, ചിത്രം വരയ്ക്കുക, പാട്ട് പാടുക എന്നൊക്കെയുള്ളത്. Now we see that AI is writing poems, it is writing stories, like very novel, new stories. They're not copying from anywhere. It is writing stories. It is creating its own music. It is generating movies. Okay. Even actors are getting replaced. It is creating new interior designs. Clothing brands are using AI to design their clothing brands. So we can see that something called creative intelligence has also evolved recently. Okay. So all these is very new to us, and all this comes under the term generative AI. And LLMs forms the backbone of this generative AI, and that's why we are here to learn about LLMs. Okay, so if you look at the larger picture, there is artificial intelligence, and you know what is artificial intelligence. This is your second day, so I'm pretty sure this was covered in the previous day. So AI is making machines able to do tasks which normally requires human intelligence. Okay. It's a very broad definition. You may have more specific definitions, but we could say that we call a machine as intelligent when it is able to do something which requires human intelligence. And then we know there is machine learning. That is a set of algorithms where you are not explicitly programming the machine to do something. The machine is learning by itself from the data, just like human learn from experience. a doctor, a very experienced doctor, is considered a very intelligent because he has seen lot of patient cases. So similarly, a machine learning model is trained on a lot of patient data that it can act as a expert doctor. Right? Then there are deep learning models. Okay. Okay, so it doesn't work. It's not working. Yeah. Then there are deep learning models where you don't have to do any explicit feature engineering. That means now you are not telling the model that these are the features, these are the properties, or these are the characteristics you are looking to data. You're just telling the model, this is the data. This is my expected output. Can you learn a pattern from this? Okay. And nor you, nor the model know how it is able to map these or what are the features that it is mapping to the output, but it is automatically learning by itself. Instead of a human or an expert telling the model that these are the symptoms that you have to look into the patient, which are relevant, so that you can identify a disease. Okay. Early machine learning models was like that. Okay. I said machine learning models learns by itself from the data. There was something called feature engineering where you had to tell what are the important features. Okay. If you are not explicitly telling it, there were algorithms, there were statistical techniques using which they could actually figure out the relevant features from that. But when the deep learning era came, even that was not required. The raw data was fed into the deep learning models, and it was by itself figuring out the features. And then to some extent, we could say it was cheating, okay, because we didn't know what features it was looking into. So there are a lot of stories about how deep learning models were cheating humans and fooling them by looking into very subtle, unnecessary data and mapping this unnecessary features and mapping it to the output so that it gets the output correct. So the concentration was only on the, and that is the reason why many hallucination happens, but whatever, we will not go into that details because our aim is not that. Then there is a very large area called natural language processing, which deals with how to understand how to understand natural language text, how to generate language text, and how to make it useful for various tasks. So again, that's a large area, and you can see there is a very heavy overlap now between AI and NLP, even though they both are two different things. Okay, NLP deals with only language processing, but AI is much broader. Using AI, you can process anything. And then similarly, there is a computer vision, just like NLP is for language, computer vision is for images and videos. So this is the overall picture, and this small spot here, you can see large language models. So it's a set of algorithms, you could say, at a very broad sense, or to just zoom in, you can say it is a set of machine learning techniques. Of course, now it is mostly deep learning techniques, algorithms that makes all this possible, and it can be applied. It comes fully under deep learning. It is mostly inside NLP, but even though it is inside NLP, it is not pure NLP. LLMs are not pure NLP any longer. But the idea of language modeling came from the concept of language processing. But now the thing is only in the name, okay? Large language model. So that word language is there only in the name, but it has outgrown from that. We'll see all of this. Okay? So we'll start with evolution of LLM because we need to know the root. By the way, is there any non-Malayalis in the group? So that I can, again, audio is breaking. Oh, sad. 8 minutes ago.
Oh, ma'am, it's clear.
Now it's clear. Okay, thank you. So is there any non-Malayalis in the audience? Yes. Okay, that yes for not for the audio or for the non-Malayali? Once more. Any Vanilla, ma'am, are you a non-Malayali? Okay, I guess all are Malayalis. So maybe I can, yes, okay. Okay, fine. We'll stick to English itself. So let us take some moments to understand how we reached here. Okay. As I said, in 1990s, we had statistical language models. Okay. Mostly it was based on statistical phenomena, statistical. Oh my God. Ma'am? Okay. Thank you. So statistical language models was in 1990s. So when I say language models in 1990, it's not your ChatGPT or Gemini or anything. These are models which are used to, these are basically probabilistic models to find probability of a sequence of words. Okay, we'll come to it later. So there was Ngram language models. Then in 2002 came mother of all this, neural language models, where instead of using statistical equations, we were talking about neural networks. We are using neural networks to model language. Then in 2013 came the word-to-vec model. Word-to-vec model is something that is used to convert text into vectors. Vectors is nothing but a list of numbers. So all of you are from computer science background. Are you? Even if it is not, it's fine. In machine learning techniques, you would know that we need to represent everything as numbers. Okay. No matter whether you are processing an image or an audio signal or a language text, everything has to be converted into vectors. Okay. And word2vec is an algorithm from Google that allows you to do so. Okay. So in 2014, so now word2vec was again a very huge revolution. Word2vec algorithm. Actually, it is not one algorithm, it's two algorithms. Skipgram algorithm and continuous bag of word algorithm. These algorithms were used to convert individual words into vectors. So when I say I love India, it will be three vectors. One vector for I, one vector for love, and one vector for India. So every word, each word would be converted into a vector. And this three vectors, if I want to feed I love India into my model, I'll be converting these three words into vectors and then feeding into the network. Then in 2014 came RNN and LSTM. Again, those are deep learning models. We are not going deep into it. Then came the attention mechanism. And finally, in 2017 came the transformers. Okay, so again, this is the second revolution. If I say the first revolution happened here, word2vec in 2013, which allowed you to convert each word into vectors, semantic vectors. And then in 2017 came the transformers, where you could do it in a more vector efficient way. The main difference is in word2vec, these vectors were static. Okay, what is static vector and a dynamic vector? When I say static vector, once I train a model, okay, once I train a word2vec model and I assign a vector to a word. So let us say I'm assigning one vector, some vector like this, to the word India. This doesn't change. Okay, so this is vector 1, 2, 3. This doesn't change. It is static. Whereas transformers use a very intelligent mechanism called self-attention, where these vectors keeps on changing according to the context. Okay, let us say I ate an apple. Okay, now apple has a vector. I work at Apple. And again, the words are same word. I ate an apple. I worked at Apple. These apple, even though they are the same word, we know they have different meaning. And how do we know they have different meaning? Because of the context, where you have used it. In one, the context is eat, and in another context is work. So when the context changes, the meaning of the word also changes. So transformers allowed you to create dynamic vectors based on the context. So in that case, both apple would get different vector representation. So this is the second revolution that happened. Okay, so after transformers in 2018, there were different variations of that model or that architecture being pre-trained and released by different people. You know, BERT was released by Google and GPT was released by anyone? Anyone can tell me? Can you tell me who's the owner of GPTs?
OpenAI.
OpenAI. Okay. So OpenAI, it is around the same time. In 2018, both was released around the same time. And this was such a wonder because, see, NLP is generally considered as, see, till now we are talking only about NLP, okay? Here, nowhere we are talking about any other form of AI. Right from 1990, where we had statistical language model, till 2018, it was only about languages. Parallelly, other researches were going on. In image, lot of ImageNet was there, AlexNet was there, like lot of advancement was happening in images. Similar process was happening in audio research, in bioinformatics and every area. They were coming up with their own models. And language models was something, or transformer was something very personal to NLP people. So in 2018, when BERT was released, it was such a huge surprise for the NLP people. At that time, I was doing my PhD at NIT Calicut. And like I was working on multiple problems. My area was in LSTM. See, the 2014 is when I started my, actually 2015 is when I started my PhD. So at 14, RNN and LSTM was released. So for the like 3 or 4 years, I'm working on 3 years, yeah. 3 years I'm working on RNN and LSTM, trying to bring like 2% improvement. Those who are doing PhD here would know that, right? Or you're trying to bring some minute change in a big, huge mountain. Okay, trying to place small stones and trying to make something of your own. And then this BERT just on an October 2018 night, I still remember that night because I was sitting in my lab and this paper was released. And in every NLP task, okay, so when I say NLP task, these are some classical problems: sentiment analysis, right? A lot of language inference, paraphrase detection, sentence similarity tasks, like there are a lot of classic data sets, classic language problems out there. And in this single paper, solved almost all these problems. And the improvement was not like 1% or 2% improvement. Improvement was like 16%. Okay, I'm telling you, 16%. And very tough problems like machine translation. Machine translation is considered as one of our most difficult tasks. Then there was question answering system, there was dialogue system. In every NLP task, and in a single paper, they released all the results in a single paper. And all from 9% to 16% improvement was there. Like the least improvement was something around 8 or 9%. And the best improvement was like 16%. What I'm telling is, a task which had only 80% accuracy, suddenly the accuracy is 96%. A task which had about 85 or 90 accuracy, suddenly it was 100% accuracy. And this brought about a very huge revolution. And pre-trained models was something that was very new for the NLP people. So ImageNet and AlexNet and all was already there in image. They were already using image processing, like pre-trained models for image processing. For NLP, this was something very new. And this, the whole history of NLP changed with this one paper, 2018, and everyone doing NLP research, PhDs, they were wondering now what else to do. Everything is gone. All the work we have been doing, many people have been working for like 6 or 7 or 8 years on a single problem, trying to bring in like 2% improvement on that. And suddenly everything has changed overnight. Then after 2018 to 2019, if you look at it, you can see there is an explosion of papers. From BERT, there was like legal BERT, financial BERT, that BERT, the bio BERT, legal BERT, like different variations of BERT. Uncountable number of BERTs were getting released day by day. And there was nothing changed. The same architecture, the transformers was being plugged into different applications. And suddenly it was solving every problem out there. which was anywhere related to NLP. Okay, wherever text was being used, wherever language text was being used, this was happening. Right. And then after that, like around 2018, GPT-2 was released by OpenAI. Then 2022, GPT-3 was released. And again, a very huge, I don't know whether you should call it revolution. Maybe we can call it a revolution. 2020, like somewhere in between 20 and 22, another thing happened. It was instruction, like it was when that generation happened. Okay. Till then, it was solving language understanding problem. See, what is language understanding problem and language generation problem? You are given a text and you have to find out whether it is a positive sentence. A review, you're given a review. You want to identify whether it is a positive review or a negative review. What kind of problem is that? It is language understanding, right? And till then, people were working on language, mostly concentrated on language understanding problem. Even question answering was not answer generation. So answer would already be there in a paragraph. You'll be giving a question along with the paragraph to the model, and model will correctly point out the starting word or position of the starting word where the answer begins and the position of the ending word where the answer ends. So mostly it was not, it was like it was extraction rather than generation, extracting the answer from a given paragraph. So exactly the sentence is being picked out from the paragraph. It is not generating a new answer. But around this place in 2022, that was when ChatGPT was released. And ChatGPT, usually we call it 3.5. Okay. Immediately before ChatGPT, there was a model called InstructGPT, which is the base of ChatGPT actually. So instruction GPT was instruction following model. Okay. Instruction following model means you can instruct the model to do something, and it will do it for you. So I'm giving a paragraph and I'm saying summarize it, it will summarize for you. I'm giving a review and saying find the sentiment of this, it will give you a sentiment. So whatever instruction you give, it was able to follow that instruction. So that was again a huge thing that happened. And after 22, everything else changed. LLM began from NLP, it began to flow into other areas like vision, bioinformatics and all other areas, speech processing and all. And LLM began to take over every single area. And now whatever we see around us, the credit goes mostly to LLMs. So we'll discuss some major breakthroughs that happened during this time. That is, this time means between 2022 and 2023. First is from the text completion models, we shifted to instruction following models. Okay, this happened because of something called reinforcement learning from human feedback. So about pre-training and instruction alignment steps, maybe we'll come to this later. So what is pre-training and instruction alignment? But before that, I think this is not the place to introduce that. Okay. So reinforcement learning with human feedback, that is, the model is now, initially LLM was meant to just complete a sentence. Okay, when you type something, again the voice is breaking, so it's so sad why this is happening. Okay, I think maybe the internet is not very smooth. That is the only thing that I can guess. Okay, am I audible now, ma'am?
Yes, ma'am.
Okay, thank you. In reinforcement learning from human feedback, see, initially the models were trained only to complete a text. But later, we reinforced, using reinforcement learning, we tried to align it to the human instructions. We'll come to this later. Then another major shift was moving from model-centric to data-centric models. Before that, like when I was doing research, before 2023, I would say, we were mostly concentrated or interested in improving the model architectures. Every researchers who are working on this machine learning or deep learning area, they had some domains. They had domain knowledge. People in working on bioinformatics may know more about genes. Music may know more about ragas and things that they do. And they were trying to adapt these machine learning algorithms and models to their domains by trying to change or bring in something in change in the architecture. Okay. Or we could say it was more like theoretical research. Okay, finally what we do is we apply it and we get the result and we say that we found something very great thing. But the thing was that people understood what is happening inside the model. They were trying to bring in some mathematical equations or formulas. They were trying to bring in some changes in the model architecture and trying to come up with new models. Even my research is a variation of LSTM. Okay, it's actually a core change in the architecture of LSTM. But after that, what happened is we shifted. There was a shift in focus from model centric to data centric. People started working on, so model is now fixed. All the things that you see around here, the basic model behind that is transformer, which we will be seeing shortly. Transformer architecture. So the model is now locked. It is the same. It's the same transformer architecture. But now we are working on what kind of data. See, same transformer, you put it on music, now it is music generation. You put it on some genes and something, and now you are talking about generating new compounds. Or you're putting in some chemical things and you're trying to generate new chemical compounds. You're trying to find new drugs. Okay? You're trying to generate new musics. So that it is now more on data centric. That's a huge shift. Then became the reasoning models, okay, where we started thinking of, instead of just giving answers, can the model do reasoning? See, that is how that theorem proving and all came into being. Now the model can not just only give you the answer, it can tell you this is the reason why this is working. You're telling the model that if I say 5 plus 3 is 8, and I'm asking you what is 12 plus 3, the model, instead of just generating an answer, it is able to give the correct reason behind these answers. And then, as I said, the language shifted to multi-model. Today's LLMs works on different kinds of data. Okay. So I have been talking a lot about language models, like language model can do that, language model can do this. But actually, what are language models? Now I'm going to take you back to the core, which is NLP. Okay, we are going to talk about pure NLP here, because as I said, the origin is from NLP. So if you want to understand what language model is, you need to know what LLM was doing in NLP before it came out and started attacking the whole world. Language model, okay, large, the term came in later. So language model is just a machine learning model that aims to predict and generate possible languages. Okay, I have highlighted this in blue color because what is the meaning? What do you mean by possible languages? So I'm just saying something like green ideas is sleeping furiously. Something like that. It doesn't make any sense, right? Each of the word are meaningful, but now I'm saying some, I'm just connecting some words and generating a sentence and it doesn't make sense. Okay. So language model, what it tries to tell you is, given a sentence, it would be able to correctly predict probability of that sentence. Okay. Am I being clear? Or to be make more clear, I'm saying I ate an ice cream. I'm saying I ate an ice cream. It is a very possible sentence. I'm saying I ate a computer. You see the difference, right? When I say I ate an ice cream, it's a sentence that has higher probability than a sentence I ate a computer or I ate a car, jeep, or something like that. So a language model is basically what it does is it takes a sentence as input and it will generate a probability for that sentence, depending on how possible that sentence is bound to occur in an actual word. So the term large comes from three factors. One is size of the model. Okay. So these are some of the famous models that I have put in here. You can see that Elmo is the first language model. Okay. Large language model is Elmo. It is not transform based. Elmo was 24 M. 24, sorry, not 24, sorry, 94 million. M stands for million. So starting from 94 million parameters from GPT-1, which was 117 million. Then we had BERT, both of them came at around the same time, 340 million. And now we can see, we are talking about, forget about millions, we are talking about billions. We have 562 billion models. And we even have larger models because here I have given only 4. This is a pretty old diagram. Large language models are pretty large models. Okay. And how does this language model works? Okay. So it estimates the probability of a token or a sequence of token based on its context. Okay. So this is a typical example of language modeling problem. So given, suppose I'm giving this 6 sentence to a language model, which one do you think will get higher probability? Jane went to store. Yes, I think number 1 will get the highest probability, right? So if we're supposed to assign a probability score for each of the sentence, as a human, as a person who knows English, I am able to assign a probability to each of this. Just like that, that's what a language model also does. It is assigning a probability to a sentence, P of text. And how does it do this? It is done based on its context. So suppose we are giving us a text like x1, x2, etc., xn, and you want to find P of x1, x2, etc., xn. Statistically, how do you do this? It's like P of probability of first word into probability of second given the first word. So I'll give an example, it will be more clear. So sentence is I love ice cream. Okay. How do you calculate the probability of the sentence I love ice cream? So you need to know what is the probability of I, what is the probability of I into, the second term will be probability of love. Second term will be probability of love. My pen is love given I. Okay. Then the third term will be into probability of ice given I love and probability of cream given I love ice. Okay. So each probability of each word is calculated from the previous words. And this previous word forms the context. Just like I said, I love, what did I say? I ate an apple has more probability than I ate a computer. How is it calculated? The probability of computer is of apple coming after I ate. Got it? So based on the context, the probability is calculated. Okay. Yeah, the same example which I said, the student opened their dash. So using a language model, what you can do is, given this as input, the student opened there is the input to your model. The model can generate probability for each of these words. Okay. So what is the probability that the word book will come after in this place? What's the probability that laptop will happen? what the probability that exam will happen? What the probability that mind will happen? Okay. What's the probability that each of this word can occur in this gap? That is what the language model is trying to figure out. And how does it figure out? How does it know that? From its training data. So depending on what your training data is, okay, and it's not something, a magical thing that is going to automatically figure this out. It is trained on very large data, the entire data in the internet. Okay, every blog that is ever written, every post that you have ever made, every book that was ever published, all this data is being used to learn this probability. So basically, do I have a figure there? I think I have a figure. Yeah, I'll come to it later. So language model does this, it is going to predict probability for each of this. And then the second task is, from this probability, you have to find a word to fill in here. Okay. So language models can again predict probability of sentences also, like if there is 2 sentences, here you can see, how are you this evening? Has your house ever been burglared? How are you this evening? Fine, thanks. How about you? We know that the second sentence has more possibility of occurring in a conversation. So you should be assigning more probability there. Okay. So LLM, again, language models were used for many other purposes also in NLP. In NLP, when we are translating words, or translating text, English to Malayalam translation, Malayalam to Hindi translation, we were using this probability to find out which is more correct translation. For example, in Malayalam, Velliyechi, okay, Velliyechi is elder sister, but Velya has other word meanings also. Velya could be large, Velya could be huge, Velya could be big. So there are multiple ways you can translate it, right? You can translate it to elder sister, you can translate it to big sister, huge sister, like that. But which is the correct translation? It is elder sister. How do you choose it? Choose this. You can use language model here. You can just translate it into different sentences, then calculate the probability of every sentence, and then you can pick the sentence which has the highest probability. Just like here, it says strong wind and large wind. Strong wind is correct. Spelling correction. See, when you're typing something into your Google search bar, when you're typing something into your Google search bar, you will see that Google is asking you, did you mean? And then it will give you a corrective. Even though you type something wrong, Google is asking you, did you mean this? And it will search for that instead of your actual text. How is this? Again, it is the use of language model. Okay, I'm talking about this like 20 years back. Google was doing this. It's not something new. They were using language models. Then speech recognition. You can see when you're talking to your Google voice search or Amazon Alexa or Google Siri or whatever, sorry, Google Home or Apple Siri or whatever, you can see that while you are talking, it is actually, the text keeps on changing. Okay? Sometimes it will make a mistake and suddenly immediately it will change it to the correct one, depending as it gets more and more contexts. So for speech recognition, then for summarization, question answering, handwriting recognition, everywhere this probability is being used. You are writing something, it is very ineligible. Okay, let us say we always correct student answer sheets, right? In student answer sheet, sometimes the student is writing in very bad handwriting. You are not able to read it. Okay, so you are trying to know, did he write receive or reconcile or resheet? What is this? I cannot read, but because from the context you are able to correctly, at least you are able to predict or estimate that maybe the student has written this word. Okay. How are you doing it? From the context, from the previous word and the next word, you are trying to assume or just trying to estimate that this is the word the student has written. Same thing is happening here. Okay. Based on the context, the model is trying to assign a probability and then to each of the possible answers and trying to choose the one with the highest probability. Yeah, this example which I said, you can see in Google when you're typing itself is giving multiple options here. In your keyboard, I will meet you at. You can see the keyboard is suggesting cafe, airport, office, home. Again here, it is language models in action. This is not magic. This has nothing to do with neural network or anything. This is pure statistics. So as I said, till now, language models was being used like that. Then came the generation part. People started using the same technique to generate text. So what you do is, first you give the first word as input, and based on the probability, you select the second word. So you decided the second word is student. Now you give this as input, the student. Based on the probability, choose the third word. Now give all the three words as input and predict the fourth word. Now give all the four words as input, predict the fifth word. If you keep on continuing this, you can use a simple language model to generate text. See, you can see how this idea of generative AI and text generation came into being. So actually language model was nothing but a model that could tell you probability. But now using this probability, people started very intelligent way of doing it. They started using probability to generate text. പണ്ടാരോ പറഞ്ഞ പോലെ ഭൂഗോളത്തിന്റെ സ്പന്ദനം കണക്കിലാണെന്ന് പറഞ്ഞ ചാക്കമാഷ് പറഞ്ഞ പോലെയാണ് ഇവിടെ. അതായത് ശരിക്കും പറഞ്ഞാൽ ഒന്നുമില്ല, പ്രോബിലിറ്റി കാൽക്കുലേഷൻ ആണ് ഇവിടെ നടക്കുന്നത്. പക്ഷേ the same technique is being used to generate text. Now, how is it being able to predict this probability? That is where the neural language model comes in. Okay, you can think of neural network as just a function f, a function that takes an input, that takes a text as input, and the function is going to predict a series of probabilities, a list of probabilities, or you could say probabilistic vector. Okay, so the input is an entire sentence, and output is multiple probabilities. Okay, what does this bar tell you, anyone? So vocabulary here, vocabulary refers to the dictionary. I'm not saying dictionary, but I'm saying vocabulary because vocabulary depends on the application or the domain you are working on. If you're working on a legal domain, there will be many legal terms in the vocabulary. You're working on a biological problem, most of the vocabulary will be some name of some genes or a medicine or something like that, right? So what this function f does is, it will take a sentence as input and it will say cat has 0.7 probability, fish has 0.2 probability, like that. For each word, it will predict a probability. This is what a neural network, this neural language model does. And, I'm not, again, you might have already learned in the previous day that you can, if given an input and output, you can actually train a neural network to map this input X into an output Y. Okay. That is some basic thing that neural network does. If you give a set of input X and the corresponding output Y, neural networks can be trained to map each of these X into corresponding Y. That is what neural network does. So a neural network was used to actually map each of these into corresponding output. Again, one interesting thing you have to note here is this a supervised learning or unsupervised learning? Anyone? Is this a supervised learning task or unsupervised learning task? Hope I'm audible. Anyone? Input is the sentence and output is a list of probabilities where each probability will tell you the chance of that word occurring there. So I have a dog whose name is Lucy and I have to dash. Okay, self-supervised. Okay. Supervised. This is supervised task. Supervised means you need labeled data, right? Yeah, supervised task is machine learning systems has labeled data. But how do you get, yeah, the first person who said self-supervised. Why it is called self, not just supervised? You can just unmute and reply if you know. Or if anyone else want to reply, you are free to do that. All of your answer is correct. It is a supervised task because there is both an input and an output label for this. But how do you get this label? Do I need a separate set from the training that the model learn itself? Yeah, every machine learning itself. See, every machine learning model is learning from the training data. So here also your answer is correct. It is learning from the data. But why is that? How is it different from another supervised learning where there is no self? It is not self. See, sentiment classification, I have a sentence and I have a label positive. And then I have another sentence which is labeled negative. So do I need a separate label here? It only learns from the input sentence only. Yeah. Okay, I think that answer is much closer. Okay, thank you for all the answers. And others who are wondering what it is, I understood. Those who have replied, they know the answer already. For the others, see, I don't need a labeled data set to train this model. Unlike a supervised learning problem, where I need to have input and I need to have a separate label for each of the input, here I need only the input sentence. Suppose my input sentence is, I have a dog. Okay, what I'll do? I will take I have as my input X. So this I will wrap this off and I'll use red color to show the input. So this, it is not working. Okay. So I have is my input X. And my output, what should be the output? My output is a probability vector, right? Output is not dog. Output is, if this is the input X, X is actually, I'm saying it is a sentence, but actually these words first will be converted into vectors and that vectors is being fed into the model. And output of the model is also another vector. And I said it is a probability vector. So what I can do is, I can suppose this is dog. This is dog. So for dog, I'll put, why I read this not working? Okay. For dog, I'll put 1. For everything else, I'll put 0. See what is happening here? So you don't need a training data for this. Only thing that you need is you need sentences. You need lots and lots and lots of sentences, which is actually very freely available there in the internet, in digital form, which you can use. Okay. So given a text corpus, that's what NLP people call it. Given text corpus, you can just take any text and convert it into a training data. Okay. You just use a sliding window approach. You take the first n words as input, and then the n plus word, you have to convert it into a vector. A vector means it is a one-hot vector where all the values will be 0, and there will be just a 1 corresponding to that word. Here, if dog is the nth word we want to predict, that has to be 1. Everything else has to be 0. See, that is why we are calling it self-supervised, because there is no separate labeled data required for this. Okay. Unlike a supervised learning where there is an input data and as well as an output label, we don't need a separate output label. We don't have a separate output label. The output label is actually within the input sentence itself. So take a sentence, convert it into an input and output. This is basically what happens in the pre-processing step. And then you give it to the model and ask it to predict the correct value. 1 for dog and 0 for every other word. 0 for cat, 0 for fish, 0 for frog, but 1 for dog. The model will be making mistake. It will be predicting different values here. Instead of 0, it will be predicting 0.1. it will be predicting 0.5 or something like that. Then you will be using a backpropagation algorithm. You will be tweaking different neuron values, weights, adjusting the weights of the network until your model learns to do the correct prediction. Okay. So this is neural language models, and this is the basic behind all this transformer. And transformer is again a neural language model. Okay, that's a doubt. By any chance, will there be two words with the same probability? Okay, very, very interesting question that is it possible that two words can have same probability? Theoretically, yes. But in reality, most probably won't be happening. Okay. But theoretically, why? Yes, definitely it is possible, right? Why wouldn't two words have same probability? But we are talking about millions of tokens, and practically there is very, very less chance that it can happen. ഒന്നും രണ്ടും പ്രോബിലിറ്റി അല്ല. We are not talking about 100 words or 200 words. We are talking about millions of tokens here. Okay. And the chances of two having the same labels is such very, very less. ചെറിയ ഡിഫറൻസ് എന്തായാലും വരും. Also called as conditional generative. About that we are always on what decoding strategy your model is using, it will choose either of this. Audio is gone again. Oh, this is so sad. Can anyone please reply? Is it only for Ala? Your voice is breaking, ma'am. Something to do with the internet. Okay.
No, ma'am.
Still
Voice is clear. Audible.
breaking.
No, ma'am.
The issues with it is something internet. That what this is the previous case. Based on the word you are choosing the large language models are trained on it's a even though the large language models are pre-trained only to predict next word, it is learning lot of useful language because it is trained on data and all this information. See, suppose you are using a physics textbook to train a model, naturally it will learn physics, won't it? When we were in first standard, we have written down in like question answers multiple times. Okay, so we were actually learning physics. We were not just learning how to write the sentences, isn't it so? Even though you are learning to write a language, you are learning to produce a language, you are also understanding the language, you are understanding the content that is contained in the language. Okay, so it is gaining a lot of information. Language model plays different roles. It is a judge of grammaticality. That means it will give higher probability to proper grammatic sentences. It is a judge of semantic plausibility. It will we assign higher probability to sentences that are more meaningful. It will enforce a stylistic consistency. It would be a repository of knowledge and knowledge also, because let's see, now instead of Google search, we are doing ChatGPT search, right? Even though it is just generating language, it is a collection of knowledge also. Again, there is no guarantee in that. Okay. So many tasks can be turned into tasks of predicting. So language model, as I said, it is good at generating probabilities. It is trained only to generate probability. It is not trained for doing something great or some magic. It is trained only to predict probability. But most of the tasks, we can convert it into probability prediction task. For example, you want to do sentiment analysis. Okay. So I want the sentences, I like Jackie Chan. If you want to find the sentiment of I like Jackie Chan, you can convert the input into like this. You can just convert the input sentence into the sentiment of the sentence I like Jackie Chan is. Right? And then you can calculate what is the probability of the word positive after this, what is the probability of the word negative after this. See, after this, many things else can come. I like Jackie Chan movie. I like Jackie Chan actor. I like Jackie Chan films. So there are multiple things that can come. But you're rephrasing it into sentiment of the sentence, I like Jackie Chan is. And then you are calculating probability of positive. You are calculating the probability of negative. And then you are just comparing which one is higher probability and choosing the correct sentiment. So most of the tasks can be converted into this format. Question answer. Who wrote the Origin of Species? Okay. You want to find the answer to this. You can convert this input into a different format. You put a question mark, a Q and a colon here, and then put a question mark here. And after question mark, you put A stands for answer, A and colon. And you give this as input. So it is going to predict high probability for the word Charles. The second step, you take the Charles and add it to the input. And now the input is Q, who wrote the Origin of Species? A, Charles. Now it has to predict the second name of Charles. So now again, it becomes a probability prediction problem. Like that, everything can be converted into probability prediction problems. So now how LLMs, I think I'm a bit running behind time. I'll make it quicker. So how does an LLM work? This is the overall flow. You have a sentence as input. First, you do tokenization. That is, you split the sentence into multiple tokens. In earlier times, when we say tokenization, it was word tokenizer. That means you're converting this into words. But nowadays, in modern LLMs, there is no word tokenizer. It's always about subword tokenizer. Okay. Suppose there is a sentence, jumping. It will be two tokens, jump and ing. Again, how is this token decided? That is a story for another day. Today, we don't have time for that. But you just have to know that tokenization does not mean word tokenization. It is, in modern NLP, it is always subwords. Okay. So the input is Paris is the city and dash is like we want to predict the next word. A tokenizer is first splitting each of this into separate words, here words or tokens. And then each of this token is assigned a token ID. Okay. There is nothing special about these numbers. 1652 does not make any sense. No meaning in that. It just means that in the vocabulary, this is the index of your word. So every word is converted into tokens, IDs, numbers. This numbers is represented as one-hot vectors. This one-hot vector goes into the LLMs. This LLM, okay, whatever I said, inside some magic is happening, not magic actually, some matrix multiplication, huge matrix multiplication followed by nonlinear activation. Functions like tan h, പണ്ട് 5ാം ക്ലാസ്സിൽ ഒരു ആവശ്യമില്ലാതെ പഠിച്ച സാധനം tan h, sigmoid, softmax, all these functions are happening inside the LLM, and then it is going to output a series of numbers which we call as logits. Okay. Logits is nothing but a series of numbers which is going to be fed into softmax function, and softmax function converts softmax function converts it into probabilities. Right? So now Paris is a city, and here you can see the highest probability, that is 0.337, is assigned to the word of. So the output will be of. Paris is the city of. Now you have to give this again as input. Again, it will predict another word which will be generated as output. This is how an LLM works. Okay. So tokenizer, yeah, the example given here, character level tokenizers are the, word level tokenizers are the, and there are subword level tokenizers. Okay. Then tokens being converted into IDs. After that, this number, token ID, converted into a one hot vector, which is one hot vector means all zeros and just one corresponding to that index. Here the index is 168. So 168 will have a number 1. Right? Goes into an embedding table, which is nothing but a matrix. So here 168 will be the 168th column in that matrix. You will be wondering, where did this matrix come from? Actually, this is a learnable matrix. This matrix represents weights of your neural network. And you know, during training, the weights are optimized, right? Weights are changing constantly during the training, and at the end, there is optimal weights. So this 168th column now optimally represents the meaning of that word. So it converts it into a vector embedding, and this vector goes to the decoder. So what happens at the decoder? Decoder, as I said, it is generating a set of probabilities, and from the probabilities, it has to choose the most appropriate word. Now, how do you go from probability to the next word? So I said, okay, this much I have already said. There is a linear layer, softmax, tokens, probabilities are generated, and there is a decoding strategy which will predict the next token. Some of the common decoding strategies are, the most common and the easiest way is greedy sampling. That means you choose always the word with the highest probability. It's a very bad option, but the easiest option. The problem with greedy sampling is, when, see, the model is only trying to find the word with the highest probability. It has no idea about English.
Hello, ma'am.
Okay. Sorry for that. I think the internet disconnected in somewhere, some point of time. Thanks for pointing it out. And happy that you all are listening. Otherwise, you wouldn't have noticed, right? Okay, now I'm back, right? You can hear me? Still can't hear?
Yes, ma'am. Yes.
Okay. Yeah. Thank you. Okay, greedy sampling. We said that after the probability, we have to choose a word. Greedy sampling is one way of doing it. You always choose the one with the highest probability. Easy way to do. Then there is beam search. Beam search means instead of choosing one, you always choose a k number of samples. And then in the final step, you can decide which one you have to go with. Then there is random sampling. Random sampling allows you to be more creative. Because
Slide is not there.
Slide is not there? Okay. So greedy sampling, then beam search, then there is random sampling. It's better to have random sampling because it allows your model to be more creative. See, you don't want your ChatGPT giving you the same answer every time you ask the same question. Right? അങ്ങനെയാണെങ്കിൽ നമ്മുടെ എല്ലാ കുട്ടികളുടെയും അസൈൻമെന്റ് ഫോട്ടോസ്റ്റാറ്റ് കോപ്പി ആയിരിക്കും. അങ്ങനെയല്ലല്ലോ. Every time the student is asking a question, ChatGPT is giving different answers because it is doing something called random sampling. In random sampling also, there are different ways to do it. There is top K random sampling, and then there is nuclear sampling. Then there is temperature settings. We'll very quickly, we'll go through this. So random sampling means, I'm sorry, greedy sampling means it's always the highest sample that is being chosen. Random sampling means every word has a probability of being picked. So based on this probability, it will be picking this one of the word from the list. We don't want a pure random sampling because see, there will be some very stupid words also which should not occur there. But when you are doing purely random, there's a chance that word also may be chosen. So what we can do is we can adjust this randomness. We can adjust this randomness by deciding how many words has to be considered. So let us say top K sampling. That means we can set the value of K. When I say K is 2, out of all these probabilities, you choose the top K. Here it is 2. So the highest is very and good. The dog is dash. The dog is dash. The highest is very and good. Out of these 2, you randomly pick 1. Okay. So out of the top K, you randomly pick 1. That is called as top K sampling. Then there is top P sampling. Top P sampling means instead of having a fixed number of K, because we don't know what is the fixed K we want, right? What happens if you choose a very large K? What happens if you choose a large K? Anyone? Suppose I'm saying K equal to 20. In this case, that means out of the top 20 words, you can choose anyone. What's the problem with that? Anyone?
The sentence meaning can sometimes go completely wrong.
Yes, very good. See, if you are allowing any 20 words can occur, then maybe the last words are very meaningless. Okay. But if I say only top 2, that means always only the 2 words will get selected. Again, that is also not good. We want diversity, but we don't want to compromise on quality. So the value of K is very important. But how do we choose K? Again, that's another question to be answered. So for that, what we do is we go for top P sampling, where we set the value of P as something. So I'm setting the value of P as 0.96. That means it will take the top K words whose probability sum up to this P. So here you can see, to get 0.96, I have to add these three values. Only if I add these three values, I will get 0.96. If I set P as 0.95, if I set P as 0.95, then I have to take only the first two values. If I set P as 0.8, if I say P is 0.8, I have to take only the first value. First value itself is 0.81. So depending on the value of P, this K will keep on changing. So this is a better way to sample. This will ensure that low probable words does not creep in. So that is top P sampling. Then there is something called temperature. Okay. Temperature allows you to change the probability distribution. Suppose this is the actual probability distribution that you got. If you decrease the temperature, okay, your probability distribution will get more and more steeper like this. Okay. This is the actual one. This one is the actual one. Okay. You are decreasing the temperature. That means you are adjusting that probabilities. You are adjusting the probability of every token and it becomes steeper. Now I'm saying take one with P equal to 0.81 or 8, then only one word is getting selected. If you increase the temperature, what is happening? The probability begins to flatten out. To flatten out this probability, more and more words get the chances of getting picked up. Okay. So if you want to be very creative, you go for high temperature. And if you want always very stable, only accurate answers, you want lesser probable words to be left out, you go for low temperature. Again, this is something which you can always set. Okay. Now, coming quickly to the transformer architecture. Till now, we have been talking about language models. We talked about what is language modeling problem in NLP, how NLP people were using it to find the probability of text. Later, how that using that probability, we started generating text, and later how every problem began to be converted into a next word prediction problem. That is what we discussed. So everything I said that there should be some algorithm to spit out this probability, and that someone is transformers. Okay. The architecture behind GPT, the transformers, it was introduced by this paper, Attention is All You Need. It was in 2017. And if you want, you can be proud because of these authors, two are Indians. The first author, Ashish Vaswani, and Nikki Parmar, is a lady. He's a boy from BITS. Ashish is, I shouldn't call him a boy, okay? But I think he'll be much younger than me. So this Ashish Vaswani is alumni of BITS planning. And Nikki is from some very ordinary engineering college, okay? Not like IITs or NITs, ordinary people who went abroad to do their PG after their BTech here and the PhD. And they are the two authors of this paper, Attention is All You Need. And people don't talk about it much. But like there are always people making fun of like America has that, they have this. What is India's contribution to AI? I don't know whether this is much of a contribution, but at least we are like, we teachers should be proud that we are teaching students who are capable of going out and producing papers that can change the entire world. Okay, I think we can always be proud that these two authors, and especially the first author, is an Indian. And so this is the paper which changed the world. Everything generative AI which we see comes from this architecture, transformers. Okay, transformer is an encoder-decoder model. Again, we are not going into any of these colorful boxes you see on the screen. Maybe some other day, some other time, but not today. So this is the actual transformer. There's an encoder and a decoder. Encoder takes a sentence as input, convert it a series of vectors. Okay. And this vectors goes into the decoder, and decoder will start producing answers. Based on the probability, it will start producing answers. So this is the classic encoder-decoder model. Not just transformer. Every encoder-decoder model follows this approach. There is an encoder for converting text into vectors, and there's a decoder which will use these vectors to generate a probability and choose a word from it. After 2017, when the transformers were introduced, in 2018, this transformer is just an architecture, right? Google took the encoder of it and trained it on very, very, very large data on their very, very huge computational power. They ran it for 5 days, burning equivalent fuel to run 5 jet planes. And then they released BERT model. So when I say BERT is not actually an architecture. BERT is actually a pre-trained model which has all this knowledge from the vast data it has been trained on. Okay? But nowadays, BERT is used, BERT style architecture. People would say BERT style architecture. Some would just, it has become common usage when I say BERT architecture. But what it actually means is it is the encoder only part of transformer. Then there is OpenAI, who took the decoder part and then trained it alone and generated it with the name GPT. Now they are going into court and saying that they want property right on GPT and others should not use the term, and all those things are happening. Earlier back then, it was not like that. So BERT is the encoder only part of this. In this transformer is this entire thing. BERT is a model of Google that was trained only on encoder, and GPT is again OpenAI model which was trained using only the decoder. And then Google again had encoder-decoder model called T5, which is using the entire architecture and trained on a large data. So training an LLM, I think tomorrow you will have more detailed class about fine-tuning and all. So I'm just giving a very basic introduction. Usually this training has 2 major cycles. The first cycle is called pre-training. It is computationally very expensive. It needs huge number of iterations and trained on huge data. And this is a self-learning or self-supervision, not self-learning, self-supervised learning. Because, as I said, it is learning just to predict the next token. So the purpose of pre-training is to teach the model understanding. Okay, basically, it is to understand the language. A large model which is trained on all English data will learn how to read and understand English. It is just like, let us say, from first standard to +2, we are learning so many things, right? From that knowledge, you can say we are being pre-trained on vast number of data. Most of the data we may not need at all. But by learning that, we are gaining the capability to understand and process things, process knowledge. Okay. So these LLMs, by pre-training, they have this capability. They're building the capability to extract information from the text. And once they are trained, they can later be fine-tuned, which is rather a cheaper process. They can be fine-tuned for very specific domain or for specific task. Okay. So this is basically, this pre-trained models are what we call as foundation models. Again, that's a very recent term. Earlier, people didn't use all this. But it's a very recent term called foundation models, which are pre-trained models for very generic tasks. Okay, they are not specialist in anything. Just like a +2 student or a degree student who have not done a PG, he have a lot of knowledge, but he's not trained for any specific task. Doctor Marake, specialization in cardiology, surgery, fine-tuning, the actual task-specific capabilities are being done at fine-tuning. Again, there are different types of fine-tuning. Fine-tuning, again, also can be same as pre-training also. Fine-tuning can be many other ways also, okay? That I think you have a separate session for that, so I'm not going into this. For pre-training, you need large corpus, and for fine-tuning, you need very small label corpus. And there is one thing I didn't mention here, which is instruction tuning. See, ChatGPT is an instruction tuned model. So after fine-tuning, there's a third step, where it is taught to follow instructions. That is where that reinforcement learning part comes in. About the three models, GPT, BERT and all. So GPT is a decoder. See, the major differences, one is architecture difference, because GPT has decoder only, BERT has encoder only, and T5 has the both part. One difference is in the architecture, like half of the architecture is only being used. Another major difference is on the task they are trained. BERT stands for bidirectional encoder representation from transformer. That's a full form of BERT. See, BERT is trained on masked language modeling, MLM. MLM stands for masked language model. Just as the name indicates, you can see here there's an input sentence, and you can see that some of the words are masked. Mask means some of the words are covered, just like fill in the blanks. When you teach a student, LKG student, some English sentences, and you are asking him to fill in the blanks. Cat sat on the dash, and he should be correctly able to write mat there. That is the task on which BERT is trained. So here the semi-supervised or self-supervised learning is not next word prediction, it is master word prediction. And then after pre-training, BERT has been learned to do so many other things. Okay. So that is masked language model. You can see some of the words masked here. Then another thing where BERT was trained is next sentence classification. Next sentence classification means there will be two sentences, sentence A and sentence B. Two sentences will be concatenated together with the SCP separator, and it is given to the BERT, and it has to predict yes or no, whether it is a next sentence or whether it is not a next sentence. That is next sentence classification or next sentence prediction task. So BERT was trained for these two things, master language model and next sentence classification. With the pre-trained models ആണെന്ന് പറഞ്ഞു, pre-train ചെയ്യണമെങ്കിൽ ഒരു ട്രെയിനിങ് ഒബ്ജക്റ്റീവ് ആണല്ലോ. ആ ട്രെയിനിങ് ഒബ്ജക്റ്റീവ് ആണ് ഇത് രണ്ടെണ്ണം. But after that, it can be used for any task like classification, question answering, many other tasks. In a single paper, multiple NLP problems were addressed. So BERT is now mostly used for feature extraction. So the idea is, given a text, if you have a text, you can just give it into a BERT, and BERT will generate it sequence of, so BERT is an encoder. So what does an encoder do? It will take sentence as input and it will convert it into a series of vectors. And those vectors can be used as features for your other task, whatever you're doing. Classification ആണ് ചെയ്യേണ്ടത്. The first part is to convert the sentence into vectors. And for that, you can use BERT. BERT, there were two models released, BERT base and BERT large. BERT base is 12 layers and BERT large is 24 layers. So their parameters are also different. BERT base has only 110 million parameters. Large has 340 million parameters. See, look at the data that is trained on. Book corpus with 800 million words and English Wikipedia with 2,500 million words. This much number of words were used to train this. It was very expensive, and to train this, Google came up with its own hardware, and that hardware is called as TPUs. Okay. Before that, we have heard about only GPUs. We know what is CPU, we know what is GPU. Google came up with a new architecture called Tensor Processing Unit, TPU, and BERT was trained using that TPU, 64 TPU for total 4 days. It was, okay, 1 day is 24 hours. So you know how many hours it was trained on. So advantages, this pre-training is done only once. Then it can be used multiple times. Okay. There are many variants of BERT. If you're interested, you can go and check. There's BERT, there is Robert, Distelbert, Albert. This is just a few, multiple other things are also there. Then coming to GPT. GPT is decoder only model. So decoder only model means it will generate one word at a time. Remember, job of the decoder is to generate one word at a time. So it was trained only for next word prediction. Given a sentence, it has to predict the probability of next word. Again, GPT also can be used for multiple tasks. It can be used for classification. Even though you say it is next word prediction only, it can be used for classification. Given a sentence, it will at the last layer you will put a classifier, and whatever is being generated from the decoder will go into the classifier, and classifier will classify it as whatever label it want. Okay, so for multiple like entailment, similarity check, can use two GPTs and generate vectors for two sentences, and then give it to a classifier and generate whether it is similar, paraphrase, plagiarism, and all you can check using that. Again, it can be trained on multiple things. Okay. So fine tuning LLM, it's I think that's a separate class, so I'm not going into that. Then before we stop, the last topic, risk of large language models. So I think it is mandatory. This session is very mandatory in every LLM class. LLMs can hallucinate. Hallucination is not something to be taken lightly. It can very convincingly say many things, which is very, very, very difficult to understand. Okay, when hallucination happens, it will be so convincing that we may feel that it is correct, and can create a lot of problems. See, earlier in our MTech presentation, some students were presenting slides, very beautiful slides, and the reference list, there were a lot of papers, okay, with paper title, journal name, year, author name, DOI, everything. But there was no paper existing, no journal of that name, no paper of that name, but it was completely hallucinated. Then LLMs are trained on many data, and they never got permission to do any of this. So there are many copyright issues happening. Then there is many privacy issues, toxicity and abuse happening. A lot of misinformation is being used, is being spread using LLM. So there are a lot of risk and safety concerns regarding this. There are many researchers going on this also, but maybe we will talk about in some other day. Just I wanted you to know there are some risk involved. So thank you for staying. And still there are 145 participants. Happy for that. So is there any doubts or anything that you wanted to discuss but I have left out? Okay, thank you. You can see some thank yous coming in the chat box. Okay, someone has to share the feedback link. Yeah, yeah, tell me.
Yeah, I'm a research scholar in FISAT.
Okay.
So most of the transformers that are available, they are the pre-trained models like BERT and all. So
Yes.
we don't have actually got anything to do in them. It's just like plug and play. Whenever you do have to do something, you just get that model from the Hugging Face library. You can do whatever you want. So is there any scope for non-pre-trained transformer models while I'm working with?
Okay, so you want to train a model from the scratch. That's what I understand.
Yes, yes.
Yeah.
Transformer from scratch. Are they relevant?
If you're asking me, is it possible? Theoretically, why not? Practical, if you look at the practical aspect, see, when you're doing research, always you will be being compared with some other things, right? Some others' work, some other values. You're saying I'm getting an accuracy of 64, then your guide is going to ask you, or rather not just guide, everyone is going to ask you, what is the state of art?
Mm-hmm.
So most of the time, these pre-trained models, not most of the time, always the pre-trained model is going to have an upper hand on your task.
Yes.
If you ask me whether it is possible, of course, there is just Google implementation of transformer from the scratch. I saw a GitHub repository where I think it is from Sebastian, Dr. Sebastian. He has an implementation in GitHub. Okay, like where he has.
If
I'm asking, like, will you be able to
specific something?
Once more.
But what if the task is domain specific?
Yeah, that's it. Like that is what I was coming to. See, if your problem is so specific, domain specific, and you feel that you are doing it from scratch would be better, definitely you can try it out.
Okay.
Because this is being done on a very general data, right?
Yes.
Nothing specific. The pre-training is very generic. Okay.
Yes.
But if you feel that your problem is that specific, none of the information which is already there is not going to help you.
Yes.
You can definitely try it out. Okay.
Yes.
But what I'm saying is that most of the time, the competition is going to be very tough because retrained models may do better. But I remember one of my colleague who was working on image processing, and in her paper, she has claimed that she got better results from ImageNet, better result than ImageNet, because ImageNet was a pre-trained
Yes.
image model. Okay, and in her paper, she was claiming that she got better results because her problem was that specific. If your
Okay.
problem is that specific, you might get better results. But if it is not the case, you will find very difficult in convincing your reviewers why you didn't go for a pre-trained model. Okay, all the best.
Yes, I
So
understand.
what is the domain, Paul, right? What's your domain?
Yes. Yes, I started this research with NLP. Then I tried with transformers. So when I started with BERT-like models, I as a researcher I didn't find much to do there. Rather than making use of it for an application, I couldn't do much with BERT models. So I thought about making a model from the scratch.
Okay.
Yes,
Okay,
thank you.
Okay. Okay. So many thank yous are there in the chat box. Thank you all.
Any other queries?
Madam, I have a query.
Yes, ma'am.
Madam, you were mentioning about fine tuning of the models, and most often what we are seeing is we'll be doing this. We'll be taking a pre-trained model and we'll be performing our data done, and finally in the last part only we'll be doing sometimes we'll be doing the fine tuning. So is it like that? It is not like only if we perform the fine tuning we'll be getting the accurate results. No, if we are still doing the normal model, we are not supposed to get the accurate results. That's what you're trying to say.
No. Definitely no. See, most of the time fine tuning, okay, thanks for bringing up the question. It's a very relevant question because is it always true that fine tuning is going to bring in better accuracy? No. So there are different types of fine tuning, and in most of the time, when we fine tune, we will stick to one or two layers. Okay, and why we are doing this is because this model has already been trained on very huge data. Fine tuning is being done on very small data, and something very dangerous. It is called as catastrophic forgetting. Okay, you can just go and Google that. It can happen. That means the model can forget what it has already learned. And if something like that happens, your model is going to perform very badly. Okay. Students have this very wrong conception that always fine-tuning is going to bring better results, which is very wrong. See, the model has already been, yeah. This is a simple example where BERT is being used for classification. Okay, so BERT has 300 and in this, is my screen visible?
Yes, ma'am. Yes, ma'am.
Okay, this is a typical example of using BERT for classification. So BERT has 340 million parameters, which it has learned from very huge data. Now you want to use BERT for a classification problem. Any classification problem. What you're doing is you are adding an additional head. We call it as a head. Okay. What it is just an additional layer called classifier layer, which will take one vector. One vector is the first vector called CLS. This vector is called CLS. You can see it is an additional token added in front of the sentence. And this first vector is taken and given as input to the classifier, and the classifier now has to predict spam or not spam. So now you are fine tuning it. You're fine tuning it for classification. You are going to update only the classifier weights. See, classifier is a very, very small model because this vector is only 768. So input to the classifier is just 768 values. And that classifier will have some layers, 768 into something matrix will be there. And only that weights is being fine-tuned during this process. But if you don't know this, you are just simply updating all these layers. What happens is the model will start forgetting what it has already learned. And the performance is going to become worse than it was before fine-tuning. So fine-tuning is not always the answer. Most of the time, without fine-tuning also, it will work. If it is a very common task, like sentiment analysis and all are very, very common tasks, this data was already there in its training and it has already got enough training to do the correct sentiment analysis. Even without fine-tuning, you're going to get better results. If you do fine-tuning, but very carefully like that, you're freezing all the weights and updating only the classifier, you will get good results. But if you try to see larger the model, larger the training data that required. We always say that deep learning models need huge training data. Why do you say that? Because this data required for learning is directly proportional to number of parameters it has. So if the model is very large, it need to be trained on very large data. Fine tuning is always done on a very small data. That means it should be used only to update few neurons. Don't try to update all the weights using a very small data, then already learned weights is going to get destroyed. If that was your question. So whenever you're fine tuning, you are just going to add few additional layers, or sometimes instead of adding additional layers, you will freeze multiple layers and keep just some layers for open for training. There's an option called freeze, where you can manually set different layers to freeze. Got it?
Okay, ma'am. Thank you.
Okay. So fine tuning again, a detailed full session on fine tuning is going to happen tomorrow, I guess. That's why I did not cover it in detail. Whenever you're fine tuning, again, most of the students, when they come for presentation, they won't do a comparison of this. They will just fine tune it and tell us that, ma'am, I got this much percentage accuracy. And we will be asking, what was your initial accuracy? Oh, I didn't check. That should never happen. Before fine tuning, you have to evaluate it on your data set and figure out what is the actual score that you're getting. Only then do the fine tuning, because you need to know whether you are doing good or bad. Already അറിയുന്ന മോഡലിനെ നശിപ്പിക്കുകയാണോ ചെയ്യുന്നത്, അതോ ശരിക്കും ഫൈൻ ട്യൂണിംഗ് കൊണ്ട് നിങ്ങൾക്ക് എന്തെങ്കിലും ഗുണം ഉണ്ടായിട്ടുണ്ടോ എന്ന് അറിയണമെങ്കിൽ ഫൈൻ ട്യൂൺ ചെയ്യാത്ത മോഡലിന്റെ റിസൾട്ട് ആദ്യം എടുത്ത് വെക്കണം. അതുപോലെ എത്ര ലെയർ ഫൈൻ ട്യൂൺ ചെയ്യണം എന്നുള്ളതൊക്കെ നമ്മുടെ ഡിസൈൻ ഡിസിഷൻ ആണ്. ഷുഡ് വി ഗോ ഫോർ 1 ലെയർ 2 ലെയർ, അതോ ഓൾട്ടർനേറ്റ് ലെയേഴ്സ്, അല്ലെങ്കിൽ എപ്പോഴും ഇനീഷ്യൽ ലെയേഴ്സ് തൊടാത്തതാണ് നല്ലത്. ഓൾവേസ് ഫ്രീസ് ദി ഇനീഷ്യൽ ലെയേഴ്സ്. എപ്പോഴും ഫൈൻ ട്യൂണിങ് ചെയ്യുക ലാസ്റ്റ് ലെയേഴ്സോ അല്ലെങ്കിൽ ലാസ്റ്റിന്റെ മുന്നിലത്തെ കുറച്ച് ലെയേഴ്സ് മാത്രമായിരിക്കും. Okay, any other questions?
Yes. മാം, അപ്പൊ ഇപ്പൊ ഒരു പ്രീ ട്രെയിൻഡ് മോഡൽ ലൈക്ക് ടൈനി ബർട്ട് അങ്ങനെ എന്തെങ്കിലും നമ്മളൊരു സെന്റിമെന്റ് ക്ലാസിഫിക്കേഷൻ ടാസ്കിന് യൂസ് ചെയ്യുവാണെങ്കിൽ, ഇപ്പൊ ഒരു എക്സിസ്റ്റിംഗ് ഡാറ്റ സെറ്റ് നമുക്ക് നെറ്റിൽ അവൈലബിൾ ആയിട്ടുള്ള ഡാറ്റ സെറ്റില് അതിനെ ഡയറക്റ്റ് നമ്മൾ ഇവാലുവേറ്റ് ചെയ്താൽ മതിയോ? ഡയറക്റ്റ് അതിൽ അതിന്റെ ആക്യുറസി എന്താണ്, ദാറ്റ് ഈസ് ഇനഫ്?
Enough for?
I mean, how its performance is evaluate ചെയ്യണമെങ്കിൽ, or we need to give this fine tuning?
ഫൈൻ ട്യൂൺ ചെയ്യണമെന്നുള്ളത് നമുക്ക് ചെയ്ത് നോക്കിയാലേ അറിയാൻ പറ്റുള്ളൂ. ഫൈൻ ട്യൂൺ അതായത് എക്സിസ്റ്റിംഗ്ലി പബ്ലിക്ലി അവൈലബിൾ ഡാറ്റ സെറ്റ് ആയതുകൊണ്ട് തന്നെ അത് എന്തായാലും പ്രീ ട്രെയിൻ ചെയ്യുമ്പോൾ അതിൻ്റെ അകത്ത് ട്രെയിനിങ്ങിൽ ഡാറ്റയിൽ ഉൾപ്പെട്ടിട്ടുണ്ടാവും. പക്ഷേ ഫൈൻ ട്യൂൺ ചെയ്യുന്നത് കൊണ്ട് നമുക്ക് ചിലപ്പോൾ ഉപകാരം ഉണ്ടാവും. ഞാൻ പറഞ്ഞില്ല, നമ്മൾ എഡീഷണൽ ലെയർ ആഡ് ചെയ്യല്ലേ. എഡീഷണൽ ലെയർ ആഡ് ചെയ്യുമ്പോൾ എന്താ അർത്ഥം? എഡീഷണൽ ആയിട്ട് കുറച്ച് ന്യൂറോൺസ് വന്നു. അപ്പൊ കുറച്ചും കൂടി ലേൺ ചെയ്യാനുള്ള കേപ്പബിലിറ്റി അവിടെ കൂടി. ഒരു 100 പാരാമീറ്റേഴ്സ് എക്സ്ട്രാ ആഡ് ചെയ്യുമ്പോൾ ആ 100 പാരാമീറ്റേഴ്സ് വെച്ചിട്ട് അതിന് കുറച്ചും കൂടി ബെറ്റർ ലേണിംഗ് ചെയ്യാൻ പറ്റും. അപ്പം നിങ്ങൾ ഫൈൻ ട്യൂൺ ചെയ്യുമ്പോൾ ഒരു ഇമ്പ്രൂവ്മെന്റ് ഉണ്ടാവും. അത് ഞാൻ പറഞ്ഞു, നമ്മൾ കെയർഫുൾ ആയിട്ട് ഫൈൻ ട്യൂൺ ചെയ്യുകയാണെങ്കിൽ ഇമ്പ്രൂവ്മെന്റ് ഉണ്ടാവും. പക്ഷെ നമ്മൾ അത് ഒന്നും അറിയാതെ ചുമ്മാ എടുത്ത് ഫൈൻ ട്യൂൺ കൊണ്ട് എല്ലാ ലെയറും കൊടുത്തു പോയാലൊക്കെ നമുക്ക് ഉള്ളതിനേക്കാൾ വേഴ്സിലേക്ക് പോവാം. ഫൈൻ ട്യൂൺ ചെയ്യുമ്പോൾ അത് വളരെ കൺട്രോൾഡ് ആയിട്ട് ചെയ്യേണ്ടതാണ്. അപ്പൊ എഡീഷണൽ ഒരു ലെയർ കൊടുത്തു, അത് ട്രെയിൻ ചെയ്ത് നോക്കി, എന്നിട്ട് അത് ഓക്കെ ആണെങ്കിൽ അടുത്ത ലെയറിലേക്ക് പോവാം. അങ്ങനെ വളരെ കൺട്രോൾഡ് ആയിട്ട് ചെയ്യേണ്ട കാര്യമാണ് ഫൈൻ ട്യൂണിങ്. ചുമ്മാ എടുത്ത് ഫൈൻ ട്യൂൺ ചെയ്ത് എപ്പോഴും നമുക്ക് ബെറ്റർ റിസൾട്ട് കിട്ടും എന്ന് പറയാൻ പറ്റില്ല. പക്ഷെ ഉണ്ടാവില്ല എന്ന് പറയാൻ പറ്റില്ല. സി, ഐ കനോട്ട് സേ ദാറ്റ് ഓൾവേസ് ഇറ്റ്സ് ഗോയിങ് ടു ബി ബാഡ്. ഇറ്റ് കുഡ് ബി ഗുഡ് because number of learning parameters are increasing when you are adding additional layers. Already 340 million parameters ഉണ്ട്. നിങ്ങൾ കുറച്ചും കൂടി additional parameters കൊടുക്കുമ്പോൾ ലേൺ ചെയ്യാനുള്ള കേപ്പബിലിറ്റി കൂടുന്നുണ്ട്. പക്ഷെ പഠിപ്പിക്കുന്ന രീതി ശരിയാണോ എന്നുള്ളതാണ് ഇവിടുത്തെ ചോദ്യം. നിങ്ങൾ അതിനെ ട്രെയിൻ ചെയ്യുമ്പം ഓൾറെഡി എക്സിസ്റ്റിംഗ് വൊക്കാബുലറിയെ നോക്കണം. അപ്പോൾ അങ്ങനത്തെ കുറച്ച് കാര്യങ്ങളൊക്കെ ശ്രദ്ധിക്കേണ്ട കാര്യമാണ്.
താങ്ക് യു മാം.
Ma'am, can we use transformers for image generation?
Yes, of course. That is what I said initially. നമുക്ക് ലാംഗ്വേജ് മോഡൽ എന്ന് പറയുന്നത് ഈ ലാംഗ്വേജ് എന്നുള്ള പേരിൽ മാത്രമേ ലാംഗ്വേജ് ഉള്ളൂ. ഇപ്പൊ വരുന്ന എല്ലാ മോഡൽസും നമുക്ക് ഇമേജ് ജനറേഷനും എല്ലാത്തിനും ഉപയോഗിക്കാം. നമ്മളിപ്പോ കാണുന്ന ഡാലി അങ്ങനത്തെ എല്ലാ ഇതില്ലേ, വിഷൻ ട്രാൻസ്ഫോമേഴ്സ് എന്ന് പറഞ്ഞ സെപ്പറേറ്റ് തന്നെ ഒരു സെക്ഷൻ ഉണ്ട്, വിഷൻ ട്രാൻസ്ഫോമേഴ്സ്. അപ്പം അതിൻ്റെ അകത്ത് സെന്റൻസിന് പകരം ഇവരെന്ത് ചെയ്യും, ഇമേജിനെ പാച്ച് ചെയ്യും. ഇമേജസിനെ സ്മോൾ പാച്ച് ആയിട്ട് ഡിവൈഡ് ചെയ്യും. അപ്പൊ ഒരു പാച്ച് എന്ന് പറഞ്ഞാൽ ഒരു വേർഡാ. ഇങ്ങനെയാണ് ഒരു വേർഡിനെ വെക്ടർ ആക്കുന്നത്. അതേപോലെ ഒരു പാച്ചിനെ എന്ത് ചെയ്യാം, വെക്ടറൈസ് ചെയ്യും. എന്നിട്ട് അഗെയിൻ അത് ജനറേറ്റ് ചെയ്യുമ്പോൾ ഇതുപോലെ ആ ഡീകോഡർ പാർട്ടിൽ ടെക്സ്റ്റ് ജനറേറ്റ് ചെയ്യുന്ന രീതിയിലുള്ള ഡീകോഡർ എന്ന് പറഞ്ഞാൽ ടെക്സ്റ്റ് ജനറേഷൻ ആണ്. ഇമേജ് ജനറേറ്റ് ചെയ്യുന്ന ഡീകോഡറിനെ വെക്കാം. ശരി, ഇമേജിൽ ഡെഫിനറ്റ്ലി ഉപയോഗിക്കേണ്ട. താങ്ക് യു ചമ്പക് കുമാർ ഫോർ ദ പോസിറ്റീവ് കമന്റ്. റിസർച്ചേഴ്സിന് എപ്പോഴും ഉണ്ടാകുന്ന ഡൗട്ടാണ്, ഈ ട്രാൻസ്ഫോമറിന് ഓൾറെഡി എല്ലാം ചെയ്യാൻ അറിയാം, അപ്പൊ ഞങ്ങൾ ഇതിൻ്റെ അകത്ത് ഇനി പുതുതായിട്ട് എന്ത് ചെയ്യാനാ, ഒന്നും ചെയ്യാനില്ലല്ലോ എന്നുള്ള സ്വാഭാവികമായിട്ടും ഒരു ഡൗട്ട് വരാം. സി, ഇതൊരു ടൂളായിട്ട് നിങ്ങൾ കാണുകയാണെങ്കിൽ ഈ വെക്ടർ ജനറേറ്റ് ചെയ്യാൻ, അതായത് ഫീച്ചർ എക്സ്ട്രാക്ഷനെ LLM ഉപയോഗിച്ച് ആ കിട്ടുന്ന ഫീച്ചർ വെക്ടറിനെ നിങ്ങൾക്ക് നിങ്ങളുടേതായ രീതിയിൽ വേറെ രീതിയിൽ അത് എങ്ങനെ ഉപയോഗിക്കാം, അങ്ങനെ ചിന്തിച്ചു നോക്കാം. ഡിപ്പെൻഡിങ് ഓൺ ദ പ്രോബ്ലം. ഓൾറെഡി ഇപ്പൊ ട്രാൻസ്ഫോമർ ഉപയോഗിച്ചിട്ട് ബയോളജിയിലൊക്കെ റിസർച്ച് ചെയ്യുന്നവരുണ്ടാവും. അവര് ട്രാൻസ്ഫോമർ വെച്ചിട്ട് പുതുതായിട്ട് ജീനൊക്കെ ജനറേറ്റ് ചെയ്യാൻ നോക്കുന്നവരാണ്. അവർക്ക് ചിലപ്പോൾ ഫ്രം ദ സ്ക്രാച്ച് ട്രെയിൻ ചെയ്യുന്ന തന്നെയായിരിക്കും അവർക്ക് എപ്പോഴും ബെനിഫിഷ്യൽ. പ്രീ ട്രെയിൻ മോഡൽ കൊണ്ട് അവർക്ക് ഒരു ഉപകാരം ഉണ്ടാവില്ല. കാരണം പ്രീ ട്രെയിൻ ചെയ്തിരിക്കുന്ന ടെക്സ്റ്റിന്റെ മേലെയാണല്ലോ. അവർക്ക് ജീനാണ് വേണ്ടെങ്കിൽ അഗെയിൻ ഇപ്പൊ കുറെ ജീനിന്റെ മേലെ ട്രെയിൻ ചെയ്ത് പ്രീ ട്രെയിൻ മോഡൽസ് വരുന്നുണ്ട്. പ്രോട്ടീനിന്റെ മേലെ ട്രെയിൻ ചെയ്തിട്ട്, അതുപോലെ ജീൻ അത് എക്സ്പ്രഷന്റെ മേലൊക്കെ ട്രെയിൻ ചെയ്ത് മോഡൽസ് വരുന്നുണ്ട്. പക്ഷെ അവർക്ക് അവരുടെ പ്രോബ്ലത്തിൽ സ്പെസിഫിക് ആയിട്ടുള്ളതായിരിക്കില്ല പ്രീ ട്രെയിൻ മോഡൽ ഉണ്ടാവും. അപ്പൊ അവർക്കൊക്കെ സ്വന്തമായിട്ട് ഫ്രം ദ സ്ക്രാച്ച് ചെയ്യാം. നമ്മൾ NLP റിസർച്ച് ചെയ്യുമ്പോൾ നമ്മള് ഈ LLM-നൊക്കെ ഒരു ഫീച്ചർ എക്സ്ട്രാക്ടിങ് ടൂൾ ആയിട്ട് കൺസിഡർ ചെയ്യാം. അതായത് ഈ സെന്റൻസിനെ നമ്മൾ ഫീച്ചറായി കൺവേർട്ട് ചെയ്യണം. കൺവേർട്ട് ചെയ്യാൻ വേണ്ടി നമ്മൾ BERT ഉപയോഗിക്കുന്നു. കൺവേർട്ട് ചെയ്ത് കിട്ടിയ വെക്ടറിനെ നമ്മൾ നമ്മുടേതായ രീതിയിൽ think of different ways how to make use of that vectors, which is relevant to your problem. നിങ്ങൾക്ക് പ്രോബ്ലത്തിന് റെലവൻ്റ് ആയ രീതിയിൽ അതിനെ കൺവേർട്ട് ചെയ്ത് യൂസ് ചെയ്യാന്നുള്ളത്. മുന്നേ ഞാൻ പറഞ്ഞു, പണ്ടൊക്കെ നമ്മൾ മോഡൽ സെൻട്രിക് റിസർച്ച് ചെയ്തുകൊണ്ടിരുന്നപ്പോൾ നമ്മുടെ മനസ്സിൽ എന്തായാലും നിർബന്ധമായിട്ട് മോഡലിന്റെ ആർക്കിടെക്ചറിൽ എന്തോ ചെയ്താൽ മാത്രമേ റിസർച്ച് ആവുള്ളൂ. ഓക്കെ, ഞാൻ റിസർച്ച് ചെയ്യുമ്പോഴും അങ്ങനെയാണ്. സോ ഇൻ മൈ ഓൾസോ ലൈക്ക് ഐ ഓൾസോ ഹാഡ് ദിസ് ഫീലിംഗ്, only when we do an architecture change then it can be called a research. പക്ഷെ ആർക്കിടെക്ചർ ചേഞ്ച് എന്ന് പറയുന്നത് ട്രാൻസ്ഫോമറിന്റെ അകത്ത് കയറി ആർക്കിടെക്ചർ ചേഞ്ച് ചെയ്യേണ്ട കാര്യമൊന്നുമില്ല. ട്രാൻസ്ഫോമർ ക്യാൻ ബി യൂസ്ഡ് ആസ് എ വെക്ടർ ജനറേഷൻ ടൂൾ. അതായത് ഫീച്ചർ എക്സ്ട്രാക്ഷൻ ടൂൾ. ആ ഫീച്ചറിനെ ഇനി നിങ്ങൾ നിങ്ങളുടെ ആർക്കിടെക്ചറിലേക്ക് ഇൻപുട്ടായി കൊടുക്കുന്നു, നിങ്ങൾ ബാക്കി എന്തൊക്കെയോ അതിൽ ചെയ്യും, അങ്ങനെ ചെയ്യും. As a mathematics research student, which are the relevant area to do with this context in algorithmic perspective rather than architecture side? Mathematical research student, okay. Mathematical research students എനിക്ക് തോന്നുന്നു നിങ്ങൾക്ക് ഒപ്റ്റിമൈസേഷൻ നോക്കാം. ഓക്കെ, ബേസിക്കലി ഇത് ഫുൾ മാത്സ് ആണ്. ഇതിനകത്ത് നമ്മൾ ഈ ലാംഗ്വേജ് ഇമേജ് എന്നൊക്കെ പറയെങ്കിലും ഇത് അടിമുടി മാത്സ് ആണ്. ഞാൻ പിന്നെ ഇന്ന് മാത്സിലേക്കൊന്നും കിടക്കണ്ട എന്നുള്ള ഇതിലാണ് അതിനെക്കുറിച്ചൊന്നും ആ ഏരിയ തൊടാതിരുന്നത്. അപ്പം ഇപ്പൊ ഒരുപാട് മാത്തമാറ്റിക്സിന് റെലവൻസ് ഉണ്ട്. കാരണം നമ്മുടെ മോഡലിന്റെ മെയിൻ പ്രശ്നം എന്ന് പറയുന്നത് സൈസ് ആണ്. ഓക്കെ, ദിസ് ഹാസ് വെരി ഹ്യൂജ് മെട്രിക്സ്. ഇതിനകത്ത് നടക്കുന്ന ഫുൾ മെട്രിക്സ് മൾട്ടിപ്ലിക്കേഷൻ ആണ്. അപ്പൊ നമ്മളിപ്പം ആലോചിക്കുന്നത് ഇത്രയും വലിയ മെട്രിക്സ് ആവശ്യമുണ്ടോ? ഓക്കെ, അപ്പൊ മെട്രിക്സ് മാത്തമാറ്റീഷ്യൻസ് എന്താണ് അതിന് പറയാം? കമ്പ്യൂട്ടർ സയൻസുകാർ പറയുന്ന ടേം ആയിരിക്കില്ല. മെട്രിക്സ് ഡീകമ്പോസിഷൻ അല്ലെ? നമുക്ക് ഈ വലിയ മെട്രിക്സിലുള്ള ഇൻഫോർമേഷൻ എങ്ങനെ ഒരു ചെറിയ മെട്രിക്സിലേക്ക് കൊണ്ടുവരാം എന്നുള്ളത് മാത്തമാറ്റീഷ്യൻസിന് റെലവെന്റ് ആയ പ്രോബ്ലം അല്ലേ ആണെന്ന് തോന്നുന്നു. ഞാനൊരു മാത്തമാറ്റിക്സ് റിസർച്ചർ അല്ല, പക്ഷെ എന്നാലും ഞാൻ മനസ്സിലാക്കുന്നത് അത് മാത്തമാറ്റീഷ്യൻസിന് വളരെ റെലവെന്റ് ആയ മെട്രിക്സ് ഡീകമ്പോസിഷനും എങ്ങനെ റാങ്ക് കുറച്ച മെട്രിക്സ് ഉണ്ടാക്കാം, അതൊക്കെ ഇപ്പൊ തന്നെ ഭയങ്കര ഫേമസ് ആയിട്ടുള്ള ലോറ, ഓക്കെ, ലോ റാങ്ക് അപ്രോക്സിമേഷൻ. ലോ റാങ്ക് അപ്രോക്സിമേഷൻ ആണ് ഫൈൻ ട്യൂണിംഗിൽ ഉപയോഗിക്കുന്ന വളരെ പോപ്പുലർ ആയിട്ടുള്ള ഏറ്റവും പോപ്പുലർ ആയി നിൽക്കുന്ന ടെക്നിക്കാണ് ഇപ്പൊ അത്. LORA, ലോ റാങ്ക് അപ്രോക്സിമേഷൻ. അതായത് നമ്മുടെ ഈ LLM ലാർജ് സലീൽ, യു ആർ എ മലയാളി റൈറ്റ്? സലീൽ, ക്യാൻ യു ഹിയർ മീ? ആളില്ലേ? ഓക്കെ, ശരി. അപ്പം നമുക്കിപ്പോ ഈ ഹ്യൂജ് മെട്രിക്സിനെ എങ്ങനെ അപ്രോക്സിമേറ്റ് ചെയ്തിട്ട് ലോവർ മെട്രിക്സിലേക്ക്, ലോവർ റാങ്കുള്ള മെട്രിക്സിലേക്ക് കൊണ്ടുവരാം എന്നുള്ളത് ഒരു എക്സാമ്പിൾ ആണ് ലോറ. അപ്പൊ ലോറ ഉപയോഗിച്ചിട്ട് വലിയ മോഡൽസിനൊക്കെ നമുക്ക് വളരെ എളുപ്പത്തിൽ ഫൈൻ ട്യൂൺ ചെയ്യാൻ പറ്റുന്നു എന്നുള്ളതാണ് കോൺട്രിബ്യൂഷൻ. അതൊരു മാത്തമെറ്റിക്കൽ റിസർച്ചിലൂടെ വന്ന ഔട്ട്പുട്ടാണ്. അപ്പൊ മാത്തമെറ്റീഷ്യൻസ് കുട്ടികൾക്ക് ഇതിനകത്ത് ഒരുപാട് കാര്യങ്ങൾ ചെയ്യാനുണ്ടാവും. എങ്ങനെ മെയിൻ ആയിട്ടുള്ള ഒരു ചാലഞ്ച് എന്ന് പറയുന്നത് നമുക്കിപ്പം ലാർജ് ലാംഗ്വേജ് മോഡൽസിന് കുറെ സസ്റ്റൈനബിലിറ്റി ഇഷ്യൂ ഉണ്ട്. ഇങ്ങനെ മോഡലിന്റെ സൈസ് കൂടിക്കൊണ്ടിരുന്നാല് അറ്റ് സം പോയിന്റ് മാക്സിമം എത്തി. ഇപ്പൊ തന്നെ നമ്മൾ മാക്സിമം എത്തി. ഇപ്പം ഗൂഗിളിനും ഓപ്പൺ AI-നൊക്കെ ഇത് അഫോർഡ് ചെയ്യാൻ പറ്റുന്നുള്ളൂ. ഒരു അക്കാഡമിക് സെറ്റപ്പിലോ അല്ലെങ്കിൽ നമ്മൾ എഡ്ജ് ഡിവൈസ് എന്ന് പറയും അല്ലെ, നമ്മുടെ സാധാ മൊബൈലിലോ അല്ലെങ്കിൽ കുഞ്ഞു കുഞ്ഞ് ചെറിയ ഡിവൈസിലൊന്നും ഈ ലാർജ് ലാംഗ്വേജ് മോഡൽസിനെ ട്രെയിൻ ചെയ്യുന്ന പോട്ടെ, ഇൻഫറൻസിന് പോലും ഉപയോഗിക്കാൻ പറ്റാത്ത ഒരു അവസ്ഥയാണ് ഇപ്പൊ നിൽക്കുന്നത്. ഇപ്പൊ എല്ലാ റിസർച്ചും ഈ മോഡലിനെ എങ്ങനെ ക്വാണ്ടൈസേഷൻ വഴി സ്മോളർ ആക്കാം, മെട്രിക്സ് അപ്രോക്സിമേഷൻ വഴി ലോ റാങ്കിലേക്ക് എങ്ങനെ കൊണ്ടുവന്നിട്ട് സ്മോളർ ആക്കാം, അതാണ് ഇപ്പോൾ എല്ലാവരും കോൺസെൻട്രേറ്റ് ചെയ്യുന്നത്. സോ ആസ് എ മാത്തമാറ്റിക്കൽ റിസർച്ചർ ഐ തിങ്ക് യു ഷുഡ് ബി ഫോക്കസിങ് ഓൺ ദിസ്. സോ ഫസ്റ്റ് യു മേ ഹാവ് ടു ഗോ ഇൻ ടു, പിന്നെ ചെയ്യാവുന്നത് ഈ ബെറ്റർ, കുറച്ചും കൂടി ഹയർ ഗോളാണ്, ബെറ്റർ ട്രെയിനിങ് ഒബ്ജക്റ്റീവ്സ്. അഗെയിൻ ട്രെയിനിങ് ഒബ്ജക്റ്റീവ്സ് ഒക്കെ മാത്തമാറ്റിക്കൽ ഫോർമുലാസ് ആണ്. സാധാരണ ട്രെയിനിങ് ഒബ്ജക്റ്റീവ് പണ്ട് ചെയ്യുന്ന ക്രോസ് എൻട്രോപ്പി ലോസ്, പിന്നെ അങ്ങനത്തെ കുറച്ച് കാര്യങ്ങളാണ് സ്ഥിരമായിട്ട് ചെയ്യുന്നത്. അതല്ലാതെ കുറച്ചും കൂടി ബെറ്റർ ട്രെയിനിങ് കൊടുക്കാൻ can you come up with better mathematical equations? You can think of it. Is it possible to create new LLM model for MRI brain tumor dataset? Is it possible to create new LLM model generating reports for MRI brain tumor dataset? Okay, brain tumor dataset ന് സ്പെസിഫിക് ആയിട്ട് ന്യൂ LLM മോഡലിന് ക്രിയേറ്റ് ചെയ്യാൻ പറ്റുമെന്നൊക്കെ ക്വസ്റ്റ്യൻ്റെ അകത്ത് തന്നെ കുറച്ചൊരു ക്ലാരിറ്റി കുറവുണ്ട്. നമ്മൾ ക്രിയേറ്റ് ചെയ്യാൻ ഉദ്ദേശിക്കുന്നത്, എനിക്ക് തോന്നുന്നത് അത് ഫൈൻ ട്യൂൺ ചെയ്ത എക്സിസ്റ്റിംഗ് മോഡൽസിനെ ഫൈൻ ട്യൂൺ ചെയ്താൽ മതിയാവും. പിന്നെ നമ്മൾ എപ്പോഴും ബേർട്ട് എന്ന് പറയുമ്പോൾ നമ്മുടെ മനസ്സിൽ വരുന്നത് സാധാ ബേർട്ടാണ്. ഈ ബയോ ബേർട്ട് എന്നൊക്കെ പറഞ്ഞ ഇതുണ്ട്. അതുപോലെ MRIക്ക് സ്പെസിഫിക് ആയിട്ട് ട്രെയിൻ ചെയ്ത പ്രീ ട്രെയിൻ മോഡൽ ഉണ്ടോ എന്ന് എനിക്ക് അറിയില്ല. ഉണ്ടെങ്കിൽ അത് യൂസ് ചെയ്യാം, അല്ലെങ്കിൽ ഓൾറെഡി ഉള്ള എടുത്തിട്ട് ഫൈൻ ട്യൂൺ ചെയ്താൽ മതിയാവും. ഈ ഒരു കേസൊക്കെയാണ് നമുക്ക് ഫൈൻ ട്യൂണിങ് ആവശ്യം വരുന്ന കേസ്. MRI ഡാറ്റയൊന്നും എത്രത്തോളം ഒറിജിനൽ ട്രെയിനിങ് ഡാറ്റയിൽ വന്നിട്ടുണ്ടാവും അറിയില്ല. അതൊക്കെ നമുക്കൊരു സ്പെസിഫിക്, വെരി ഡൊമൈൻ സ്പെസിഫിക് ആയിട്ടുള്ള നോ വോയിസോ വീണ്ടും ഡിസ്കണക്ട് ആയിപ്പോയോ? ഇല്ലല്ലോ. Okay, sorry, Vanilla ma'am, you were not a Malayali, right? Okay. Did you understand what I said? Okay. I was saying that I'm not sure whether a pre-trained model for MRI brain tumor is available. If it is not available, this is a very good use case where you can try fine-tuning it. I don't know whether you should be creating a new LLM. I think you should be taking an LLM and try to fine-tune it, because your objective is to generate reports, right? And generation part, existing pre-trained models will do it better. If there is no existing pre-trained model, you will have to go for fine-tuning. Okay, I can see some of the hands are raised. നേരത്തെ റേസ് ചെയ്തവർ താക്കാൻ മറന്നുപോയതാണോ അതോ ഡൗട്ട് ഉള്ളത് കൊണ്ട് നിൽക്കുകയാണോ? ആവാൻ ചാൻസ് ഇല്ല. പ്രണവ്ക്ക് ഇവിടുത്തെ പ്രണവല്ലേ? Seven raised hands are there. Is there any doubt? Pranav, Vinita, Sumita, Manoj. Okay, എല്ലാവരും that way. Vinita is the Vinita met. No, ma'am. There are so many things that I have not covered, especially self-attention, multi-head attention, and all those things. But see, those who are interested in NLP research, they should definitely learn all those things. For others, maybe it's not that relevant, because most of the time you are just using the model as a tool in your work. But those who are doing pure NLP research, these are the topics that you should be looking into. Okay. So this was actually meant to be a generic thing. This talk was meant to be generic. That's why I did not cover any of that.
Okay, thank you, ma'am.
Okay.
Now, I would like to propose the vote of thanks on behalf of the Department of the Computer Science and Engineering FISAT. I express my sincere gratitude to our esteemed speaker, Dr. Gina Klinakandi, for delivering such a wonderful and insightful session. Your expertise in transformers and LLMs has greatly enriched our knowledge. I extend my heartfelt thanks to the organizing committee for their constant support and guidance. I also thank all the participants for your enthusiastic participation and engagement throughout the section. Once again, thank you all for being part of day 2 of this FDP. Thank you and gave a great hit.
Okay. Thanks a lot.
Thank you, ma'am. Participants, please note the feedback link shared in the chat box only. Tomorrow's session starts at 2 p.m. We have Dr. Anilda J as the resource person and session title Domain Adaptation and Fine-Tuning and Prompt Engineering. Thank you all.
കണ്ടിട്ടൊരു മൈൻഡ് ഇല്ലാത്തത്. ഞാൻ വന്നു നേരത്തെ പഞ്ചൗട്ട് ചെയ്യാൻ സംഭവിച്ചു. പിള്ളേരൊന്നും ഇല്ലല്ലോ. മായ അങ്ങ് കൊണ്ടുവിട്ടു. തമ്പാനൂരൊക്കെ എന്താ ആൾക്കാർ റോട്ടിൽ കിടക്കുമായിരുന്നു എന്നൊക്കെ പറയുന്നു. വണ്ടി കിട്ടുമോന്ന് ഉറപ്പില്ലല്ലോ, ഞാൻ കൊണ്ടുവിടാന്ന് പറഞ്ഞു. ശരി
മാം സ്പീക്കർ ഓൺ ആണ്.